Section 2.2, Operations with Fractions. I'm going to be making the assumption in this section that there's nothing here that you have not seen before and that this is a quick review. So I just have a couple examples of each of the different situations, and I'm going to try and show you maybe a different perspective on some of these things than you've seen before. Alright, the first thing is factoring 105 into primes. This can be useful sometimes when you get in a difficult fraction situation. I think the easiest way to factor a number into primes is to make a factoring tree, where you write the number down and then you just try and think about what's something that goes into this number. And when a number ends in 5, it's always divisible by 5. So I'll go ahead and think about how many times does 5 go in there. And you could divide it out, long division. Maybe you can do it in your head. You can also use your calculator, it's fine with me. So 5 goes into 105 21 times. So you're thinking of one number that goes in, and then you're doing the division to see how many times it goes in. If a number is only divisible by 1 in itself, like 5, then that would be a prime, and you'll just bring your primes down. 21, if you can think of some other numbers that go into there, you need to keep going. And 3 goes into 21, and 3 goes into 21 7 times. And 3 is prime, and 7 is prime. So now I'm done with the work, though I haven't actually answered the question. So factoring a number into primes means to rewrite it as a product of primes. So after you've done the tree, you should write 105 is equal to 3 times 5 times 7. It's fairly standard to put the primes in order, but it's not a right-wrong issue. So if you just wrote 5 times 3 times 7, that would be fine as well. I'm not going to do a ton of factoring into primes, so I didn't do a really big number here, but it can be useful sometimes when we're trying to reduce fractions, which we'll see soon. So a prime number, which is what they're asking about here, or a prime, is any counting number larger than 1 whose only positive factors are 1 in itself. So it is important to notice that 1 is not a prime by definition. It's only numbers larger than 1. That's because they want this factorization to be unique. If you could factor, if 1 was a prime, you could keep splitting these up 1 times, and add extra 1s here and say you had a different factorization of primes, and they don't want that. So 1 is not considered a prime. Alright, let's see where that comes in by looking at these next couple examples. They want us to simplify each of the following fractions, 18 over 30 and 49 over 63. So the key here is trying to think of a factor that the numerator and denominator have in common. And a lot of times you can just think of something. So I'm looking at the 18 and 30 and I'm thinking mentally, what's the number that goes into both of these? And I'm thinking of 6. So I'm going to write the numerator as 3 times 6 and the denominator as 5 times 6, so that I'm kind of revealing that common factor that I thought of. And then what we're going to do, you won't write it out this way all the time, but we kind of think of separating that off as 6 over 6. And 6 over 6 is 1, and 1 times 3/5 is just 3/5. So if you can find a factor that's in common to the numerator and denominator, then that can be canceled out because it's just a factor of 1. So typically after I show it like that, then I would just come in and say I'm going to cancel these 6's. But really what I'm doing when I cancel 6's is getting rid of a factor of 1. So that's fine, but there's times where you look at a fraction and you're not having anything jump into your head that's in common. So this one's not super big, so maybe you're looking at it and you are thinking of a common factor, but I want to show you what you would do if you can't think of anything in common. So maybe you see the common factor already, maybe you don't. Don't worry about that. There will be situations where you can't tell what the common factors are. And what you can do in those situations is take the numbers and factor them into primes. So 49, think about primes. Do they go in? 2, no, because it's odd. 3, no, you just try it. It doesn't. 5, no, because it doesn't end in 0 or 5. 7, yeah, 7 goes in. And it goes in 7 times. So the numerator is 7 times 7. So now a really useful thing to think about here when I go to the second number, 63, is I want to reduce this fraction. That's what they mean when they say simplify, is reduce. So the only way it's going to reduce is if I can cancel something on the top and the bottom, and the top is just 7. So the only way this is going to be a useful factoring is if there's a 7 there. And 7 does go into 63, 9 times. Now you could split the 9 up into 3 times 3, and I'll go ahead and do that. It's kind of unnecessary because I can tell over here those 3's aren't going to cancel. So if I wasn't trying to illustrate this method of factoring into primes, I probably would have just stopped at 7 times 9. But I'll go ahead and write the prime factorizations on both the top and the bottom. Now, this isn't something you want to do every time. I think it takes extra time. But the idea is, if you can't see anything in common and then you factor into primes, if there was anything in common, it is going to show up. And then sometimes knowing what the primes are on one helps you think about what you should try in the other one. And then I can cancel one of the 7's up top with one of the 7's in the denominator, and then I'd take whatever's left over and I'd multiply that out. So just a 7 on the top, and the 3 times 3 is 9. So I actually could see the 7 right from the beginning. If you can see the 7 right from the beginning, you should just go straight to factoring that as 7 times 7 over 7 times 9. Cancel a 7, and the answer is 7/9. That's going to be faster than doing these factor trees, but the point of the factor trees is you'll never miss anything if you do that, right? Like nothing can hide as a common factor. So anytime you don't think you can see any common factors, if you do that, that'll help you make sure. So here's the steps for simplifying a fraction. Again, when they say to simplify a fraction, they're just talking about reducing. So it's good to understand what they mean by the terminology. And their steps say find the prime factorization of the numerator and denominator. Like they're saying you should always do that. And I would say this is something you would do if you can't see a common factor. If you can see the common factor, just split it off and cancel it. And when you're canceling, you're using this idea that if you do have a common factor, you can split it off. It's just a 1, and that 1 doesn't change anything, so it can go away. All right, so that's the process of simplifying or reducing fractions that we'll use in this section and beyond. Okay, now that we've talked about reducing fractions, we're going to start looking at other operations, multiplication, division, addition, subtraction, and so on. And they want us to do a few of those. I'm going to go ahead and just show you the steps, the way I think about this, and then we'll have kind of a summary of those steps on the next page. They also want us to check these with a calculator. I don't want to check all of them, but I'll show you what they mean. So let's take this one and we'll check it with the calculator, and let's take this one down here and we'll check that with the calculator too. So for most of them, I'll just show you the work. For those two, I'll show you what they have in mind for check with the calculator. That's an optional step that you can do anytime you're unsure. All right, so the first thing we have is 6/7 times 4/9. So when you're multiplying fractions, you've probably heard before that you should multiply straight across. So if by that we meant 6 times 4 is 24 and 7 times 9 is 63, then I would argue that multiplying straight across is a bad idea because it makes the numbers bigger and it makes it harder for you to understand or see what can be canceled. So what they really mean by multiply straight across is take all the factors in the numerator of the numerators and put them in one numerator. Take all the factors of the denominator and put them in one denominator and have them connected by multiplication. But I wouldn't carry it out until after I've thought about reducing. And in fact, I would think about reducing right away. Like, does the 6 have anything in common with the bottom? Yeah, there's a 3 in there and there's a 3 in there. So I would take that 6 and rewrite it as 3 times 2. I wouldn't necessarily factor the 4 because I don't see any even numbers down there, so I'm not going to be able to cancel 2's, so I'll just leave it alone. So I don't always factor all the way to primes. I just try and do factoring that I think is going to be useful to help me reduce the fraction. 7 is already prime, and the 9 is 3 times 3. So technically, I've already finished the multiplication problem on this because I've gone from one fraction times another to now I just have a single fraction, and it's all connected by multiplication straight across. But I haven't carried it out, which means I haven't simplified yet. So I can cancel these 3's. 3 over 3 is just 1, so I can get rid of that. And then multiply what's left over. So 2 times 4 is 8, and 3 times 7 is 21. And we've multiplied fractions. And only one example there, but we'll get another look at that when we do the next one. Because the process of dividing fractions is to change it to multiplication of the reciprocal. So we take the first part, the 5/8, and we leave it alone. And we change the division to a multiplication, and we take the reciprocal of the thing we're dividing by, officially the divisor. So in that one step, we've gone from division to multiplication, which means we're back in the previous situation. I just remember that you have to multiply by the reciprocal of the divisor when you're doing division. A little trick I've heard somebody say before is, how do you know which one is the right one to flip or take the reciprocal of? And they say the one on the right is the right one to flip, the one on the left should be left alone. So kind of a little clever wording thing there that maybe helps you a little bit. All right, so we made this a multiplication. Now I want to do the same thing I did above. I want to write the factors of the two numerators in one numerator, the factors of the two denominators in a single denominator. But I'm thinking about what can I cancel, and I see that 4 goes into 8. So I'm going to write 5 times 4 on the top, but for the 8 I'm going to write that as 4 times 2. So that kind of 4 that I could see I could cancel, I'm just making that visible so that people can tell what I'm doing. And then 4 over 4 is just a 1, so I can cancel those off. And I end up with 5 over 6. All right, so we said we were going to check this one with the calculator. So let me go ahead and show you what they mean by that. So what they have in mind is that you would take the initial problem, 5 over 8, divided by 3 over 4, and it is actually important on division that you put the divisor in parentheses. That's actually fine. It's maybe even a better idea to put both in parentheses so that you see it as one fraction divided by another fraction. It turns out it's the same. If I forgot to put parentheses at all, it does mess it up. So the parentheses are important. It turns out you only really need them on the bottom fraction, but just to be safe, anytime you have a division with more than one number, put those things in parentheses. So again, let me just pull up the one that's probably the best representation of that right there, and we get 0.83333. All right, so if that's correct, then when we take our answer, 5, 6, we should get the same thing, and we do. So that's what they have in mind when they say check with the calculator, is that you'd put in the original problem, see what it looks like as a decimal, put in your answer, see what it looks like as a decimal, and then hopefully it's the same. All right, so let's move on to some other examples. Adding fractions, what we want to do is keep the denominator the same and just add the numerators. So it looks like that. And then 2 plus 3 is 5, so 5 over 7 is the answer. I actually think this is a good one to check on the calculator too, because sometimes what people want to do is add 2 plus 3 is 5, but then also 7 plus 7 is 14, and I just want to show you which one of those is the correct method. So if I take 2 over 7 plus 3 over 7, I get that. If I take 5/7, I get the same thing. But if I thought that what I was supposed to do was add the tops and add the bottoms, I get something different than the original. So that kind of shows you it is right to keep the denominator the same. Another way of thinking about it is thinking about the names of these. This is called the numerator and denominator. The denominator tells you what kind of thing you have. Think like denomination, like dollars, $5, $20 bills, $100 bills. That's the kind of denomination. So the denominator is saying what kind of thing you have. And then the numerator, think number, it's telling you how many. So this is just a kind of thing. I have 2/7 plus 3/7, now I have 5/7. Just like if I had 2 apples plus 3 apples, now I'd have 5 apples. When you add things together, first of all, they need to be the same kind. And second of all, they don't change what kind they are after you add them. So when we add or subtract fractions, the numerators will get added or subtracted. The denominators must be the same, and they'll stay whatever they were. So same idea. We have 13/18 minus 5/18. Again, if I had 13 apples minus 5 apples, it would be 8 apples. And the same thing happens here. I don't change what kind of thing they are, so I keep them as 18ths. And I take the 13 and I subtract the 5. And 13 minus 5 is 8 over 18. On this one, unlike the last one, I see that I have stuff in common, and they do always want us to simplify our answers. So what I see that they have in common is a 2. So I'll make that 2 obvious by showing a partial factorization. Again, I don't like to waste time factoring into primes. I just like to show the number that I'm going to reduce before I do it. And then we have 4/9 left over. And there's our subtraction problem. Continuing on, look at a couple that are a little bit messier. Here we have addition, but the things we're adding don't have a common denominator. So there's 2 ways to approach this, and I'll show you both of them. The first one, which will work for most of the fractions we deal with, is, well, first of all, we have to get a common denominator. So how do you do that, right? So the first approach is just to think about it. And what you want to think about, the question you want to ask yourself, is what is a number that is divisible by 8 and also divisible by 6, and then try and keep that number as small as possible. So one thing people do sometimes is multiply these together. 8 times 6, which is 48. That will always work in the sense that 8 will go into it and so will 6, but a lot of times that's too big. So can you think of a smaller number besides 48 that is divisible by both 8 and 6? And I can, 24. So what I'm going to do is I'm going to try and make both of these have a denominator of 24. I'm going to do something that's kind of the opposite of the reducing we've been doing. I'm going to multiply top and bottom by the same number. So I'm going to think about if the common denominator I'm aiming for is 24, then what do I have to multiply 8 by to get 24? And the answer is 3. But I have to multiply the top by the same thing so that I'm multiplying by 3 over 3, which is 1. The goal is to make this fraction have the same value, but not to, but to look different, to have the denominator we were looking for, right? But not to change the value while you do that. So we still want to have the same value as the 3/8, but just look different. So on this one, same thing. What do I multiply 6 by to get 24? It'd be a 4. And whatever I multiply on the bottom, and I'll multiply the top by the same thing, so that overall I'm multiplying by 1. And if you do that, you'll have 9 24ths plus 4 24ths. Now they're the same kind, so you can add up the counts. And 9 plus 4 is 13, which is prime, so I'm not going to be able to reduce this. 13 24ths is the answer. All right, so I want to show you that a different way, but I also said I was going to check it with the calculator, so let's do that too. Go ahead and plop the calculator right into the middle here. And let's take the beginning part, 3/8 plus 1/6. We get 0.5416 repeating. And then my end answer, 13 over 24. Same thing. So it looks like that process worked. Where that process can be troubling is at the beginning I said think of a number that's divisible by both 8 and 6. Sometimes you might not be able to do that. It's not popping into your head. So I want to show you what to do in that case. Though I think mentally when you think of it, what you should probably be doing is taking the bigger number and thinking, does 6 go into 8? No. How about if I double it? 16. Does 6 go into 16? No. How about if I triple it? Does 6 go into 24? Yes. Okay, that's probably the process that's happening mentally when we do it that way. But sometimes that's still not going to come quick. So if you're not quickly thinking of a common denominator, then factor both denominators into primes. So 8 is 2 times 2 times 2. And I'm going to leave a little space. And 1/6, the 6 is 2 times 3. And the goal is to have a common denominator. So just look at these and think about what's different about the denominators. They have to have the same things in them. This one has a 3 and this one doesn't in its denominator. So if these are ever going to be the same, this needs a 3. But if I multiply the denominator by 3, I have to multiply the top by 3 too to keep things balanced. Now, this one has nothing to be jealous of over here. It looks over at its neighbor, there's a 2 and a 3. It's like, I have a 2 and a 3, so it's happy, right? But now we go move over to this house and look at it from this perspective, and we think about kind of what are we jealous of. So we have a 2 and a 3, so does our neighbor, but hey, they have 3 2s, we only have 1. So if we want to keep up with the Joneses or catch up to our neighbor, we would need to go out and buy a couple new 2s that we maybe don't need, right? Anyways. And if you need those 2s on the bottom, you need them on the top also. But the goal is just to kind of keep looking back and forth to see what's preventing these from being different and multiply that in. But don't forget, when you multiply it in, it has to be on the top and the bottom. And then when you do that, maybe you haven't even thought about what the denominator is, which is kind of a cool thing about this. It just kind of happens. But if you multiply those out, this is going to be your 9/24, that's going to be your 4/24, and then you're on your way. So it's a lot faster if you can just think about what's the least common denominator and it pops into your head. But that's a little trick for when you're stuck. All right, final example on this page has a whole number and a fraction. So what do you do when you have one of each? And the answer is they both need to be fractions. So make that 3/1 minus 4/5. Think about the common denominator. If one of your denominators is 1, which it is here, then the other denominator is always going to be your common denominator. So just multiply here by 5, top and bottom. When we do that, we get 15/5 minus 4/5. We can subtract the numerators to get 11, and they're still fifths. All right, so there's a few examples of multiplication, division, addition, and subtraction. All right, let's go ahead and look at some summaries of the different operations we did on the previous pages. So if you're multiplying fractions, this is saying if you're doing a over b times c over d, just make that ac over bd, which is saying multiply the numerators, multiply the denominators. So in words, if you're going to multiply two fractions, just write the numerators as a product and write the denominators as a product. Notice they're saying write it as a product, right? Not figure out the product. Don't carry out the multiplication, but just write them as a dot c, b dot d. And the other note I would add here is try to reveal common factors when you do that. So as you're getting ready to go from this step to this step, be looking at the numerators and denominators and think about, is there any common factor I can cancel? And if so, try and reveal that so people can see clearly where your canceling is coming from. When you're dividing fractions, it's a over b divided by c over d. We're going to multiply by the reciprocal of the divisor. So the one on the right will be the reciprocal, the one on the left will be left alone. And then when you're adding, you have to have a common denominator, and if you do, you can just add the numerators or subtract the numerators if it's subtraction, same idea, but you have to have a common denominator. If you don't, you have to follow the process from the previous page, one of those two processes, to come up with a common denominator. All right, so let's look at something a little different here, which is some properties of 0. So we need to remember that if 0 is in a fraction, is it a problem? Is it no problem? What do we do? So if you have 0 divided by 621, if you have 0 on top and then some non-zero on the bottom, then the answer to that is 0. Think about if you had no money and 621 people, then you're taking all that no money and dividing it equally, everybody gets no money. Whereas if you had $713 and no people, that's a confusing thing to think about what each person gets if there's not any people. So we end up saying this one is undefined. And essentially, that's just where it's supposed to stop. That if you are seeing a 0 in the numerator and a constant that's not 0, a constant in the denominator that's not 0, then the answer is 0. But anytime there's a 0 on the bottom, it's undefined. So they have that summary here. The fraction a over b is undefined if b equals 0. So no 0 denominators. If so, it's undefined. I just kind of want to show you why. So let me take another fraction, let's say 18 divided by 3, and think about what's the answer. It's 6, right? And then how do you check that? We would often say because 3 times 6 equals 18. That's fairly common that people would think about it that way to make sure they had done it right. So what if we had 0 over 3? So what's the answer? Well, according to this, it would be 0. And then if you check it, you would do the denominator 3 times your answer 0 and think about, is that equal to the numerator 0? And yeah, it is. So that one seems to make sense. What about this one right here? So what if you took 713 and you divide it by 0? What's the answer? Would say you thought the answer was 0. Well, is 0 times 0 713? No. And then what if you thought, well, there has to be some answer. In fact, I kind of made an x there. Let's make it a better x. What is, maybe I just don't know the answer, right? So let's throw a variable in that spot. What would that have to be? Well, it would have to be the case that the denominator times that x was equal to 713, and 0 times anything is 0. So there's nothing you could put there that would give you that answer. So there's no defined number such that 0 times that number is 713. So that's where that idea comes from. And the same thing is true if it's 0 over 0. That's a little bit of a weird case, but anytime there's a 0 in the denominator, we say that's an undefined case. And finally, one last example for this section. They want us to evaluate this expression, x over w minus y over z, where w is 4, x is 3, y is 5, and z is 12. Anytime they ask you to evaluate an expression, that's something you can only do if they give you the values of the variable, and you just need to substitute those values in and then simplify from there. So x, they said, is 3 over w, which they're telling us is 4, minus y, which they say is 5, divided by z, which they say is 12. And now we just have an expression to simplify, and it's a subtraction of fractions. They don't have a common denominator, so we'd want to think about what is the common denominator. 4 goes into 12. Anytime one denominator goes into the other, that bigger number would be your least common denominator. So let me just fix this up right here. I can make these the same. If I multiply the denominator by 3, this will become a 12. So I'll do that on the top also so that I'm keeping things balanced. And then I end up with 9 over 12 minus 5 over 12. That's 9 minus 5, or 4 over 12. There's a common factor there of 4. So if I show that and I cancel it, sometimes people would say the answer there is just 3. But what we have to remember is that when I say it's a 4, that's also 4 times 1. You don't have to write that 1, but you do have to remember if you cancel the whole numerator, there is still a 1 left over. And certainly 3 and 1/3 are not the same. To eat a third of a pizza is normal. To eat 3 pizzas might have a little problem. All right, that wraps up section 2.2.